All right. Good afternoon, everyone. Wow, only 4 people came to the class in person. Looks like most of you like to stay in your house or room to watch the lecture online, right? Yeah. Okay. Yeah. Then let us just take this class like a seminar. Feel free to interact with me and ask for any details. Okay. So in the last lecture, we talked about local variational inference, right? So is another type of variational inference, and the goal is just again is to approximate posterior distribution, and we use Bayesian logistic regression as one example to showcase how we apply the local variational inference to easily obtain approximate distribution, right? So I want to give kind of like summary of these two types of method, point out their connections and differences to give you a sense. But essentially, they're doing the same thing, but the way to obtain the approximate posterior is a little bit different. And in practice, of course, you can choose a hybrid of global and local variational inference. It's totally up to you. Okay. So both global and local variational inference live on the known decomposition of the log joint probability, log margin probability, namely log model evidence. Right? So we can, in January, let us assume, okay, we got a latent random variable W, right? So in my samples from some prior distribution in the given W, you observe the data D, right? And so your joint distribution is usually written as the prior of W and the likelihood of data D given W, well, the latter usually is decomposed as a product of like n data point, right? So this might be like each observed variable like be Zn given W, right? So for the logistic regression, W might correspond to the feature weights, and the likelihood might be the Bernoulli likelihood parameterized by some sigmoid function. Right? So as we discussed in the last lecture. Right? So the goal for Bayesian inference, of course, is to compute the posterior distribution of W given the observed data D. Right? So this, unfortunately, by applying the Bayes rule, is really infeasible because of this difficult integral to calculate the denominator, right? So that's why we need to seek for approximation techniques. And the variational inference use an idea that I'm gonna approximate. I want to find approximation distribution of W. I want to make it this approximate distribution to be as close to the true posterior as possible, right? So how can we find such approximation? Right? So it is based upon a well-known decomposition of the log evidence, right? By applying the Jensen's inequality. We know that this guy, it's a fixed guy, right, is essentially a evidence lower bound. Let me logarithm, log fraction. This is the expectation of log fraction of the joint distribution and the approximate distribution, plus the K divergence from the approximate posterior Q of W to the true posterior. Okay.
This equality does not need Jensen.
Oh,
it's just true.
Yeah, this is true. I mean, if you want to get
the lower bound,
you got inequality, and then you want to look at what's the gap between the evidence and this lower bound. It is called divergence. Okay, so And this guy is often called elbow, evidence lower bound. It's a nice name. So, and this elbow essentially is an expectation of this log fractional, right? The expectation is taken under this approximate posterior Q of W, right? So it's essentially expectation. So the good view is that if we do not restrict Q of W, like let me assume Q of W is free, right? You don't put any constraint, then your maximizing of this elbow is equivalent to minimize this Q divergence, right? So that means the calculation of the, when you reach the true maximum, you actually reach the true minimum of the Q divergence. And true minimum of Q divergence is achieved when your Q of W equals to the true posterior distribution, right? So you can see that if you don't put any constraint on Q of W, the maximization of this elbow is equivalent to calculating the true posterior distribution. Right? So, of course, in most of the cases, we cannot directly maximize this guy if you don't put any simplification about Q of W or other relaxation forms, right? So let us just put it aside. Right? If you don't put any constraint over Q of W, you just assume Q of W can be whatever thing you want. And suppose you're super powerful, you can maximize this elbow and to get to the global maximum. And then it is equivalent to you're able to compute the true posterior. Because when this gets to the maximum, this gets to the minimum, which is 0, at which Q of W will be the true posterior. So this is this view is also called a variational form of Bayesian inference. Why? Because the straightforward computation of true posterior, you need to do the integral, right? You need to divide the joint distribution by this integral. Now, by using a variational viewpoint, you actually turn the calculation of integral into a optimization problem. You're maximizing some evidence lower bound with respect to some unknown distribution Q of W. This is a very good viewpoint, right? But this is just like theoretical elegance, right? And because the difficulty to maximizing this guy is not smaller than directly computing the true posterior. But there's a way to reduce the difficulty in maximizing this elbow. How? We got two strategies. One is called global variation inference, one is called local variation inference. Okay? So the global variation inference, the global one is that, okay, I still maximize this elbow. I don't change the form, but I make additional restrictions on the form of Q of W. Right? Q of W is not assumed to be free form. Instead, I'm restrict the range of Q of W in a relatively simpler family of distribution, for example, Gaussian. Or you might not specify a particular parametric form, but I assume Q of W is factorized over subsets of variables. Right? This is called mean field approximation. Right? And if this depends on the problem, right? So if you can choose a simple enough structure of Q of W, and then your maximization of this elbow under this smaller range of Q of W will be a lot easier. And you can maximize this elbow to find the Q of W to be as close to the true posterior as possible inside this small family. That's what we call global variation inference. And of course, there are a lot of tricks about how to smartly extend this family of Q of W while not make this whole maximization of elbow maximization intractable. Right? And then we'll talk about another idea, which is called local variation inference. Okay? So what is local variation inference? So local variation inference means that, okay, I do not compromise the range to the range of Q of W. I still assume Q of W is free form. However, I'm going to come out a relaxation of elbow, meaning that I conduct a lower bound of elbow. Well, how to construct such a lower bound? Let us just assume we come out this lower bound. Then we maximize this lower bound instead with respect to Q of W. And we expect that by introducing this lower bound, sorry, I need to put this lower bound in terms of Q of W. And to introduce such a lower bound, you usually need to introduce an additional set of parameters C, which we often call the variational parameters. So we expect that introducing this lower bound, when you maximize this lower bound with respect to Q of W, even you do not restrict the range of Q of W, it's still pretty easy. For example, in the Bayesian logistic regression case, when we maximize the lower bound of the elbow, your optimal Q of W will be a Gaussian. But there's still price, right? Because you're not maximizing elbow. You're switching your objective to an easy form. And with the cost that you're gonna add an additional set of parameters to C. And then you need to also optimize this to C to make your lower bound as tight as possible. And of course, we call it variational form because this is a relaxation form, meaning that if you don't make any restriction on C, theoretically speaking, you can always find a value of C star such that your lower bound reaches the orange elbow. However, this is really infeasible in practice. In practice, if you want to make this whole computation, meaning that optimizing to C and Q of W both easy and convenient, you have to restrict these variational parameters. For example, to make it in a smaller family or smaller range, so that your lower bound will always have some gap between the two elbows. So now you can see the difference between the global variation inference and local variation inference.
So the solution from sourcing Q of W now is moved to the section of the space of C.
Yes. Like, what we can do like this local variation inference as a augmented approach or auxiliary approach. You're kind of introducing a set of new parameters to get a relaxation of the elbow, which is usually the lower bound of the elbow. And although theoretically speaking, you can make your C optimal enough to make this equality holds, but to compromise to the practical computation cost, you have to restrict C as well. And although under the form of this lower bound, even you don't restrict Q of W, we expect Q of W is very easy to compute. So, and how to construct this lower bound? Well, the often used technique is convex conjugate. Right? So if you can find some factor, your log joint probability has some convex form, you can apply the convex conjugate, you construct a lower bound of that factor, you shove it into your log joint probability, and you introduce additional variational parameters. So this is a difference between the global and the local version inference. Is just like two different ways to ease the optimization problem. So, and there's no free lunch. In both cases, you can see that you kind of to allow your computation easier and convenient, you kind of sacrifice some accuracy, right? In the first case, well, although I preserve the exact objective, right, I kind of restrict the feasible space or domain of the approximation distribution. And that means if your approximation family is too small, there's always a gap between your true posterior and the approximate posterior. Right? The gap can be quite large. Right? And in the local version inference, well, you construct another alternative form upper bounded by the elbow. The good thing is that, okay, you don't need to make specific restriction of Q of W. The bad thing is that you need to optimize a set of additional parameters. And also, you have to constrain this set of additional parameters as well to make the whole computation easy. Okay, so this is a high-level summary of these two types of ideas. Hope that it will give you some kind of a sense of these whole ideas. So basically, if you're doing variational approximations, that means you're gonna always have some errors. Any questions so far? Nowadays, it is more common to use global. The reason is because the development of optimization techniques make it feasible to optimize this elbow. Like you can assume Q of W has to be quite complicated for like a mixture of Gaussian or even Q of W is parameterized by neural network. It's okay. And if you want to optimize it, because this is an expectation, right? So in the stochastic optimization framework, you can calculate a stochastic estimate of this expectation, and this is like far more frequent than the local version inference in today's approximate inference area. If you do the local version inference, well, you have to find some structure or some terms inside your log joint probability that satisfy some property like convexity, right? And then you apply those tricks, and usually it's not very easy. It's not very easy. It's not like off the shelf tool you can leverage. So if we can take a look at the variational logistic regression, and at the beginning we want to take a look at the log sigmoid. Right? You want to talk log sigmoid function. We found that log sigmoid actually is concave, not convex. And then you need to do some like transformation of those terms, and found that okay, the sigmoid subtracted by half z is convex to z squared. Right? It's kind of like it's not very easy to discover. You need a lot of like insight on that. As like if you are very smart, you can do that. But most people are not that smart. So that's why right now the global version inference is more common and popular.
We use Jensen inequality to define the lower bound for like At that point, it's completely similar to what we are doing right now, because in that case we have an extra variable, and we were aware that we have equality if we maximize the lower bound. So it is very similar to that.
You mean the local and global version inference?
No, I don't even the local one. Okay. And that case, we do not use conjugate, but by using Jensen inequality, we add a new variable, And we were aware that if we maximize over that variable, we have the equality.
Oh yeah, of course. But this guy is kind of like giving you the structure to allow you to do this in this whole framework. And this guy is that, okay, under this bound, you use kind of same set of techniques to get a further lower bound to make the computation easier. That's why it's called local.
I mean, for the local one, if we have just we find a function that has an extra variable, and we know that maximizing over that extra variable gives us the original function which ends it.
Yes. I mean, and it's not necessary to use convex conjugate. There are other techniques to do that as well. But again, yours is not very easy. Yeah, you have to have some smart insight and observations on the structure of your drawing probability and factors inside that. Okay, so why is it called variational bound? The variational bound is a variational transformation. It means that if you do not restrict the range of the variational parameters, they always have a settings that reach the equality. Like here is if you do not restrict, this is a global variational inference case where if you do not restrict family Q of W, in theory, if you set Q of W to the true posterior, you get the equality, right? And here for the local variational inference, if you don't restrict to C and you assume that you're always you're able to get the true optimal C, then you can make sure that your lower bound reaches the original elbow. So that's why it's called a variational bound. But in practice, to compromise to the computation, we have to restrict the family or the range of the variational parameters to gain the computation easiness. Again, there's no free lunch. Okay, so now we can extend our variational inference algorithm to the so-called variational EM algorithm. What does it mean? It means that, okay, previously we assume, okay, if the model has some hyperparameters, we assume, okay, the hyperparameters itself are fixed or known. That means under this hyperparameters, let me put X as data. Given this is fixed, we assume this log mod evidence is always fixed, right? And then given theta is fixed, then maximizing the variational lower bound is equivalent to minimizing K divergence. And now, what if we also want to learn the hyperparameters? And here we assume like hyperparameters are just points and no random mix, and we want to get some point estimation, which is enough. How can we do that? We can simply apply the same framework as we did for the EM algorithm. So that is we're doing alternating updates of Q of Z and theta. So in the E step, we fix theta, and then we maximize the evidence lower bound with respect to Q. We got the optimal approximate posterior under the current setting of Q. That's theta hyperparameters. And in the M step, we fix the current variational posterior Q of Z and maximize the elbow with respect to theta. And you do this alternating update until convergence or the maximum number of iterations are reached. So here I want to point out that this is not equivalent to EM algorithm. So EM algorithm guarantees you're actually maximizing the true mod evidence. But for the variational EM algorithm, you're not guaranteed to maximize this guy. You're actually maximizing the lower bound of that, because this is the objective function you're working with. Because Q of Z is not, usually is not the true posterior. That means your lower bound is rarely reaching the true mod evidence. Does it make sense? So it is actually approximation. It's not like as elegant as EM. Like every time, if I can compute the true posterior on the current theta, I'm maximizing the lower bound is equivalent to maximizing this true mode evidence. And unfortunately, there's a gap between the evidence lower bound and the true mode evidence because Q of Z is not the true posterior. And then you maximize this lower bound again, and that does not guarantee every time you new up this theta will increase the true mode evidence. But this is like very, very popular in practice. The reason is that there's no other good alternatives to jointly estimate the hyperparameters and also calculate the posterior distribution. Any question?
For the Gaussian model, you are able to find to maximize the true evidence because the posterior was inside the space we are
Yes.
looking.
Yes. In that case, your Q of Z is true posterior. But as we mentioned before, right, you really have to restrict Q of Z to be relatively simple. Right? Then even your optimal Q of Z in your range, it does not necessarily. It is not necessary to be the true posterior. So that means your at that case, the Q of Z usually is not the your evidence usually does not reach the true evidence. And then you maximize this lower bound again. So then it's not guaranteed that every time you're gonna increase your true mode evidence.
In other words, it is because the second term, which was given in terms of KL divergence, cannot get zero.
Yes, exactly. Questions? Okay, looks like everyone's happy. Okay, and then we want to talk about how do we conduct variational inference on graphic models, specifically on the Bayesian networks. And it turns out that if we assume a factorized posterior over the nodes in the Bayesian networks, and the mean field variational inference on this Bayesian network corresponds to a particular message passing protocol. Of course, this is just to give you a connection between the graphic model and approximate inference. But in practice, you might not need to just draw the whole graphic model and look at how the message is sent out and integrate together. So remember, when we construct Bayesian network, when we write down this Bayesian network, we know that for each node, it is associated with a conditional distribution. If it has parents, right, meaning that the neighbor nodes which point to that node, those parents will be the conditional part in the conditional probability of xi. Right? So if you write down the joint probability, it is a product over every node in the Bayesian network. Each product term is a conditional distribution of the node xi given its parents. So if we want to compute the posterior distribution of x here are the nodes 3, x4, x5, something like that. Let us assume the posterior is factorized over every node. So Q of x is equal to the product of each factor over xi, qi, xi. And then we can apply the mean field variation update, the rule we have derived before, right? So we know that for each particular j, Q of xj, when it is updated, we should fix the factors for the other nodes. So this take logarithm of the joint probability. So by the way, we didn't explicitly write down the observed data. So we just for convenience, but you can imagine that the joint distribution actually includes the data. So you take the joint probability over all the nodes, and then you take expectation over the log joint probability. The expectation is under all the other nodes except the node G. Then you take exponential, you do the normalization. Right? This is just applying the rule of the mean field update. And then the natural question is, which set of nodes in the Bayesian network really determines the update of Q of XG? Yes, exactly right. So remember, this guy, when you decompose it, it is a summation over all the node n, right? And it is logarithm of the joint probability, or the conditional probability of xn and their parents. So know that many nodes which might not related to xj in that, for example, if some term does not contain xj at all, they're constant to xj. Right? So when you take expectation, well, you can take expectation, but when you do the normalization, they're going to be canceled out. So you can just throw them out. Right? Then the only log conditional probabilities that related to xj are those terms that include xj. Which conditional probabilities include xj? It will involve the conditional probability with xj as the major distribution, or xj in the parent part. Right? So all those set of variables in those conditional probabilities that include xj is actually the Markov blanket. Right? So if you simplify the updates of Q of xj, you see that it is proportional to exp expectation log probability of xj given the parent of xj, and also all the other log joint probability that xj serves part of the parents. Okay. So if you look at all the other variables appearing in these terms, you see that those are shaded nodes surrounding xj form the Markov blanket. So what does it tell us? If you apply this guy, this update rule and simplified update rule, you find that it's essentially a message passing protocol. I can show you how this is done. So it's better to view it as a factor graph. So let me just redraw the factor. So this guy will be factor, this guy will be factor, this guy will be factor. Okay. So let me just use green. So you got a factor here that mapping is x1, x2. Just copy here. And you got a factor here. And you have x3, x4, x5, x6. Right? So this is a x3, x4, and x6, x5. And let me denote it by f1, f2, and f3. It's very, very sloppy notations, but just to give you a sense. So, so first of all, the message from each node, each variable node sent to its neighboring factors are just the Q of xj. So the message xj sent to every factor node are all Q of xg. So it's different from the some product algorithm we introduced. We have different rules to calculate message. But here in our variational inference world, we define our own message. Our message sent from each variable node to any of its neighboring factor is just the Q of xg. I mean the proximate posterior for this particular node. And this Q of xj, before it's sent out, needs to be first aggregated from the neighboring factors. So the neighboring factors to Q of xj is proportional to all the neighboring factors belong to neighboring xj. The message sent from neighboring factors to xj and xj. So this is kind of similar to the factor to the sum product algorithm. Like if we want to get we want to receive the message, we just receive the message aggregated to xj, we just multiply the incoming messages. Right? So, and then what is the message for a particular factor to this variable xj? It is just like if you want to compute mu f1 to xg, okay? So it is just the exp and expectation of the message sent from x1, x2 to f1. That is x1, x2, and times logarithm of f1 and x1, x2, and xg. Okay. And f1 is actually the conditional probability, which is p of j given x1, x2. And remember, the message sent from x1, x2 to f1 essentially is q of x1 times q of x2, right? Because it's factorized. Then you just follow this rule to calculate the message from the neighboring factor f1 to xj. Okay. So now you calculate this, you formula the same way to calculate message from f2 to xj. You calculate message from x3 to xj. You multiply them together, you got your updated message of xj, which is going to be distributed back to every neighboring factor of xj. And if you do this together, you found that this is essentially our mean field variational updating rule. So you can see that actually based on the Bayesian network structure and our variational mean field updating rule, we can define a new message passing protocol. That is so-called variational message passing. Any questions so far? Okay, so this to give you an alternative view, like how do you combine the computation of the variational inference and also the graphical illustration and model together. But there are other message passing protocols to conduct approximate inference, like expectation propagation, which we might not be able to illustrate in our class. But later, let's see if we have enough time to introduce that. But by performing variational inference, will give you one way to the message passing. So the variational message passing tells us that the fact, given the graphing model, the mean field variation update only requires a local computation on the graph. The local computation is restricted in the Markov blanket. So now we have give a kind of like a general introduction of the variational inference algorithm. So variational inference algorithm can be viewed as built based upon the EM algorithm. But the EM algorithm is kind of like an accurate, exact inference algorithm because each time you're assuming you're able to compute the true posterior under the current model parameters, current hyperparameters, which is called E-step. Right? And if it is a case that we cannot compute exact posterior, then we come out the variational inference. Right? So the variational inference is built upon this knowing decomposition structure. That is, log evidence is the variational lower bound plus the Carroll divergence. And if you're maximizing variational lower bound, it's equal to minimizing Carroll divergence. And to give you an alternative view of the Bayesian inference. Right? the calculation of true posterior is equivalent to maximizing the variational lower bound without putting any constraint on the proximal posterior. Okay? And of course, to allow easy computation, you have either restrict the family of proximal posterior, or you got a further relaxation form of this evidence lower bound, and but by introducing an additional set of parameters. Right? The alternative maximizing the proximal posterior and the additional parameters. That is called local variation. So we hope that you know what is EM algorithm, what is global variation inference, and what is the updating rule for the mean field variation inference, and general update in the exponential family, and what's the idea of local variation inference, and the most commonly used tool to construct a lower bound of the elbow that is a convex conjugate, and some graphical insight of conducting variational inference on the Bayesian network. It's called variational message passing. And most importantly, we hope you are able to derive and implement variational inference algorithm for many Bayesian models. Okay. Any questions so far? Great. So next, we're going to introduce a very popular, very classical model to introduce this Bayesian model, Bayesian formulation, and then how we conduct variational inference for that as a concrete example. And learning this model, we'll use the so-called variational EM procedure. But the variational update is following the mean field update. So this model is called a latent dirichlet allocation, and sometimes it's referred to as topic models. It was proposed in 2003, and then it becomes very, very hot topic. And the latent dirichlet allocation paper has gained a citation like over 40K. So maybe 10 years ago or 15 years ago, it is kind of like a hottest topic in machine learning. And many every year in the machine learning manuals are a lot of like different variants of the latent dirichlet allocation models proposed. So nowadays, like with the popularity of the neural networks, the latent dirichlet allocation gradually lose the attention from the major research community, but its techniques and all kind of exploration has already been done. It has been viewed as kind of like mature tool. You'll find like in the web, you find a lot of implementations of latent dirichlet allocations, and also it's widely used in industry. Okay. And also there are some like upgraded version of LDA, like neural LDA. How do you integrate this with the neural network? And Google has its own topic models, but it's not built upon latent dirichlet allocations based upon. It's kind of other probabilistic graph models. The architecture looks like a bit neural network, but it's not neural network. So they have a very, very vague introduction of their system because they're like core top secret in their search engine, because the whole search engine, the revenue comes from how you identify those keywords, and then from huge amount of documents generated every minute from the word, and a lot of like keywords are kind of long tail. They might only attract like hundreds of thousands of users, and you need to identify those key terms so that when users search them, you can very accurately retrieve the documents which contain those keywords. This is a very, very important in the search engine system, and Google has developed their own system, but they never disclosed the details of that. And in academia, people are LDA, latent dirichlet allocation, is very popular. In that, it's very easy to compute, and very easy to deal with, and it's working pretty well in practice. So here's the brief introduction of a latent dirichlet allocation. So it's kind of like classical text mining model that extract topics from text corpus. So basically, imagine that you have a collection of the articles from New York Times or Washington Post. Right? I want to know what are the topics those articles are talking about. Like, it might talk about war, might talk about business, politics, entertainment, right? So we want to extract keywords which represent different topics from those documents. It is broadly used in all kinds of text mining and related tasks, like information retrieval, text classification, advertisement keywords extraction, right? So if you want to build up online advertising system, you need to tell your the whole advertising system what kind of keywords you believe is good, right? It's actually the design of keywords is very important. They can suggest you like good keywords, right? And sentimental analysis, right? How people feel about this type of opinions or things and so on. And here I won't click the link for this, but this is just some data about that, some benchmark data on that. If you're interested, you can take a look. And it is a very good example to study Bayesian learning. This is my first model I studied by myself to learn what is Bayesian learning, what is posterior inference. I still remember, like maybe 18 years ago. No, not 18 years ago. 15 years ago, I read through this latent directional adaptation and know what the model talks about and the whole computational procedure. I felt very excited. Okay, so one example of latent directional allocation, as we mentioned, that it wants to extract topics and topic words from the document. Right? So look at this piece of document. Right? This is the running result of latent directional allocation. So it extracts different sets of words, and each set of words represents a particular topic. Like, and they are marked by different colors. Right? Like the red words represent topic about arts. The blue represents budgets. Not blue, green. Right? Blue, children, and this purple, maybe it's purple. It's about education. You can see that on a different topic, the words, the representative words are different, right? So for arts, those words talking about arts are mostly like a film, show, music, movie, actor, opera, theaters, those kind of things, right? And for budgets, they're mostly talk about the money, right? Millions, tax, program, budget, billing, federal, and so on. Children and education is about schools, teachers, public, state, elementary, and so on. So how does the LDA model work? So the basic idea is that, okay, I'm assuming each topic are represented by the distribution of the words on that vocabulary. Assume that we got a fixed vocabulary which contains like 10,000 words. Okay? So you can imagine if you use words to generate text about some specific topic, some words will appear much more frequently than the others. Okay? Like if you're talking about arts, then the most frequent words might be film, like paint, like actor, and so on, right? So that means the distribution of the words in the vocabulary will be biased toward those frequent words, right? Like maybe the word film in its distribution will be 0.3, that is extreme, right? This might be 0.1, this might be 0.05, and so on. And for those infrequent words, their probability to appear will be much, much smaller. And similarly, when we look at the text that talk about education, right? The probability of each word that appear in that text will vary as well. And in this case, most frequently appearing words might be just college, university, students, and those words. Right? And you can imagine their probability to appear might be 0.2, 0.1, 0.3. And for the other words that unlikely appear in text, talk about education might be very low, like field might be just 0.03. So the mathematical model of these topics is that, okay, I'm gonna assume a fixed length vocabulary, right? So each token in this vocabulary corresponds to a particular word. And each particular topic is associated with a distribution of the words in this vocabulary, right? Of course, different topics will correspond to different distributions. And our goal is to learn the distributions of the words for different topics. And also, you're given a collection of documents. We also want to infer how much proportion in this particular document is talking about topic 1, how much proportion of the words in this document is talking about topic 2, and it's actually the mixtures of the topics in each particular document. Does it make sense? So this is our original paper. If you're interested, you can take a look at this. This is one of the most classical paper in machine learning. So now we want to introduce the LDA model. Right? As we mentioned, right, any Bayesian model actually defines a sampling procedure to generate the observed data. For the LDA model, the data is just a collection of the articles, a collection of documents. So you need to first specify a number of topics. So this is like clustering, right? You need to specify a number of clusters, K, beforehand. And but later for the, advanced topic about LDA, there's some probabilistic models that can automatically identify the number of topics. But here, let us just look at the simple one. We assume the number of topics K are given beforehand, which I believe from this collection of documents, we have 10 topics. Right? And then LDA will first sample the K topics from some prior, which we'll say it's from derivative prior. And of course, each topic is represented by a distribution of the words in our vocabulary. And then it's gonna, given this word distributions, they're gonna sample each document. How do we sample that? For each document, we first sample the topic mixture distribution. So topic, suppose you have K topics, then your topic mixture distribution will be a probability vector of dimension K, right? And you can imagine if K is 3, then your topic mixture distribution might be 0.1, 0.8, 0.1, right? And next topic, the next document, it might be 0.07, 0.02, 0.01. So you first sample the topic mixture distribution for this particular document. Then under the topic mixture distribution and also the word distribution for the K topics, you generate each word in the document independently. Right? So for each word, you're going to first sample the topic index for this word, namely from under which topic this word is generated. Right? You have K possible choices, right? And then given the topic's index, you retrieve the corresponding word distribution to sample the word from the categorical distribution. So you can see it's a very highly simplified model, right? It actually doesn't account for the strong dependency of the words in your sentences or in the paragraphs, right? You just assume, okay, under the topics, under the word distribution for the topics, under the topic mixtures, you just sample each word independently. You're just ignoring if a word A appears first, and how likely word B will appear. Right? So it's a very simplified model. And of course, there are more advanced versions to account for this sequential dependencies of the word. But here, let's just use the simplification, simplified assumption, which have already been very useful. Okay. Any questions so far? Okay. So now let us look at, yeah. That's very good question. So remember, when we observed a collection of documents, right? If we want to fit our model, we need to assume it is our model using some probabilistic sampling procedure to generate these observed documents. Through this sampling procedure, you might have a bunch of parameters, right? W, theta, those kind of things. Right? And then you can write down a joint probability. You sample W theta and then your collection of data, the documents D, right? Then your goal is to compute the posterior distribution of those parameters given D. Right? Yeah, that's why, I mean, given the data, if you want to fit your model, if you want to use a model to fit the data, in the Bayesian framework, you always need to assume how you generate this data, how the data was generated by a model, right? And then you can have a joint distribution to describe your model parameters and data, and then you can do some invert computation, that is to compute the posterior distribution. And of course, once you have this posterior distribution, you can use as a generative or sampling procedure to go through this sampling procedure to generate a set of new documents. That's totally fine. Yes.
Now we are using that.
Yes, exactly. Yeah. You can view it as a discrete version of a mixture model. It's mixture of it is a mixture of Dirichlet distributions. It's not a mixture of Gaussians. So now let us look at a more detailed specification of this model in the graphical representation. Right? Suppose our vocabulary has V words in total, and we have M documents in our collection, and for each particular document N, it has NT words. So in our LDA model, we first sample the word distribution for each topic K. So we denote the word distribution for topic K by beta K. So you can imagine this is a probability vector of dimension V, right? V is the size of the vocabulary, and each element in this beta K is just probability. The summation must be 1. So it is a parameter for some multinomial distribution. So we'll sample beta K from some Dirichlet distribution. I remember we talked about that before, right? If you want to sample a probability vector, a very commonly used prior distribution is Dirichlet distribution. And then to sample the whole, or to generate the whole collection of M documents, right? For each document N, so we're going to first sample a topic's mixture, namely, what's the proportion of each topic appears in this text, right? Appears document. Right? So this theta N essentially is the topic mixture vector, which is not a probability vector. And because we have K topics in total, so you can imagine theta N contains K elements. Each element is a probability, their summation is 1. Right? Again, it is a probability vector. And we're going to sample it from another Dirichlet distribution parameterized by R. And then, given the topic mixture, we sample each word in topic in the document N. Right? So we have NT words. Right? So to sample each word J in document N, we're going to first sample the topic for that word N. which we denote by Z and G. So Z and G comes from, is sampled from a categorical distribution determined by theta n. Theta n essentially just tells you what is the probability you got topic 1, what is probability you got topic 2, until what is probability you got topic k. For example, your sample theta n might be 0.1, 0.2, 0.3, 0.4, right? This is for this is your theta n, right? And now, based on theta n, you sample Z and G from the categorical distribution. So, and you might got your Z and G to be topic 3. So through the one hot encoding representation, it will be 0, 0, 1, 0. Right? And once you have remember this is a one hot vector topic index. There's only one element, 1. Right? Once you identify the particular topic the word G in document n belongs to, you can sample the word itself from the corresponding word distribution for that topic. Okay. So, for example, in this case, we know that the topic belongs to topic 3, right? Then you're going to retrieve beta 3 as your distribution for the words to sample the word. Right? Again, it's from another categorical distribution. And my observed WNJ essentially is another one hot vector, and which has only one element being 1, which corresponds to the actual observed word. And in this way, we generate one word. And we repeat this procedure to generate the next word. Again, we're going to first sample the topic index according to the topic mixture probability. And then, given the topic index, you retrieve the corresponding word distribution. On this word distribution, you sample the particular word. You do this until you finish generating all the words in document n. Then you move to the next document and sample the topics mixture, and then go through and then sample each word until you finish the generation of all n documents.
Why this procedure? It seems that we need to terminate policy.
Terminate what?
We need somehow to terminate, stop.
Yes.
What's the procedure to stop? We do that until what?
Until you sample all the documents, you need to specify the number of the.
Yeah, the number of documents is specified, but the length of the document is also a random variable. Okay?
Well, you can model the number of the words in the document, but right now the data is given. So that means the length of each document is given.
I know, but then you are defining the model.
Yeah. For defining a model, yeah, you can apply a prior over NT as well. You can apply the prior over the number of documents as well. I mean, there is indeed some model and incorporate this prior into that as well, like using Poisson distribution to sample the number of the words per document, the number of the documents in the corpus. Any other question? So this is like a structure, and then to sample the word distribution for each topic, as we just mentioned, we're going to use a Dirichlet distribution parameterized by this eta, right? And in most LD models, they assume, remember the Dirichlet distribution is actually parameterized by eta 1, eta 2, and say eta v, right? Suppose you have v dimensional, right? But here, for simplicity, they just assume all these eta values are the same parameter eta. So when you write down the distribution, you got this form, right? So it is a product over from 1 to big V, right? V is dimension. And beta kv to the power of eta minus 1, and this is a normalization factor. You have to divide the gamma function of summation of all the eta values, which is V eta, divided by the product of gamma function over each individual eta. And then for each document, if you want to sample the topics mixture probabilities, we use another Dirichlet distribution parameterized by alpha, right? And you have a k topics, so you have k alpha values alpha 1 to alpha bk. Again, you can assume all those alpha k are the same, or you can use different alpha k. Right? So, and this is also the form of the probability, form of the distribution, Dirichlet distribution. Right? And then you sample the topic index for the J's word in document N, here denoted by Z and G. Right? It is from a categorical distribution or multinomial distribution. It is actually this way, right? So the theta nk is actually the case element, this probability vector, to the power of Z and GK. Remember, Z and G is one hot encoded, right? And there's only one element is 1, indicating the selected or sample topic, all the other 0. So if Z and GK is 0, then you're just multiplying 1 here, right? And only the index which has Z and GK to be 1 to have this probability corresponding to theta and k. This is how we represent the probability of a categorical distribution. And then the word itself, WNG, is sampled conditioned on Z and G and beta. If Z and G k is 1, meaning that, okay, the topic index is k, then we're gonna use beta k, the word distribution for topic k, to sample or to generate this word, which is again, the probability is a categorical distribution. Right? And for a more convenient representation of this conditional probability, we don't want to write it as if else, right? If ZNGK1 is ZNGK1 is 1, you got this. If ZNGK plus 1 is 1, you got another this, right? You can simply write this conditional probability in one form. It's just a product from topic 1 to topic k, and the word from 1 to big V, and then your beta KV has the power Z and GK and W and GV. What does it mean? It means that if a particular topic, say 3, is sample, meaning that Z and G 3 is 1, then you can activate the corresponding beta 3V, right? Because your power, this part will be 1, and then W and GV just to tell you which particular word it is a sample. Right? And for all the other k, right? For k equals 2, for k equals to 5, those kind of things, because the corresponding Z and GK is 0. So the whole beta kV to this power is simply 1. Right? So it just automatically encode the retrieval of the corresponding topic and their word distribution to sample the word. Okay, so if we write down the joint probability, it is a bit lengthy, but it's quite structured. Right? So in our side, we're going to first sample the word distribution for all the k topics, from each of which is sampled from a Dirichlet distribution, and then you're going to go through the whole set of documents. For each document, you first sample the topic, the word distribution, the topic distribution or topics mixture through this Dirichlet distribution, and then you go through each word. Right? You go through each word. For each word, you first sample the topic, and then given the topic and the word distribution for all the topics, you sample the observed word. So if you multiply it together, it just give you this form. Okay, so this is a model introduction. Now let us consider the training or the inference. How we're gonna do that? Right? So although this looks like a big complex, at least like about 15 years ago, when I started this, I feel it's complicated. However, the computation is really easy. It's really easy. You see that in a moment. Right? So first, we need to know what is our goal, right? So given this M documents, right? A collection of M observed documents, we want to compute the posterior of beta, namely the posterior of this word distribution for all the k topics. And also we want to know the posterior of the topic mixtures for each particular document. Okay. So you can view like this topic mixture distribution is kind of like a concise summary of that document, right? Like this lengthy document. After my running of my variational inference, I know that okay, this document basically talking about 60% talking about application and 20% talking about money, and 10% talking about others. Right? They give me a very short or compressed representation of the document. That's why sometimes people usually use topic mixture as a compression or low rank representation of the documents. It's funny that in our CS department, when we look at the applications, we'll first run the topic model, the LD model, under the application documents. From that, we'll see, okay, these students are mostly interested in artificial intelligence, like 60% of artificial intelligence, and 20% about the computational architecture, and 10% others. Well, another is like, okay, maybe 80% the students his interest is in like computational security, and the 20% is talking about software engineering. Right? This will help us to quickly identify who is more appropriate to look at the student's profile. It's just an interesting application I've used. It's being very helpful. Okay. But in addition to that, we know that to generate the word distribution for the topic and also the topic mixture for each document, we have hyperparameters eta and alpha. Right? We also want to estimate eta and alpha. And here we just want eta and alpha to be a point estimation. That's enough. We don't want to assign a prior or eta and calculate their posterior. Right? So you can see that we want to learn hyperparameters eta and alpha. We also want to estimate posterior distribution for the word distribution of the word topics and also topic mixtures for each document. So we're gonna use the variational EM procedure. Right? So we know that in the E step, we're gonna update those approximate posterior. In M step, we maximize the evidence lower bound with respect to the hyperparameters alpha and eta. And here, we use the mean field variational inference. That is, we assume Q, beta, theta, and Z are factorized across the topics, and factorized across the documents, and factorized across the words. It's very simple structure we assume for that, right? So the topics, the word distribution for the topics, the topic mixtures, and the topics of the words, they're all factorized. And it's factorized across the topic, across documents, across the words. Right? Of course, this might be oversimplified, but in practice, this often works quite well. Right? So the remaining thing will be, how do we conduct the mean field update for each factor in our approximate posterior? Right? When we look at this, I mean, although you can see this kind of a two hierarchical components inside this joint distribution. When we try to update each factor, you'll see that it's pretty straightforward because because each factor is only related to a small subset of latent random variables, namely the Markov random field, namely the Markov blank key. Right? So if we take a look at how to update the topic for each particular word, like the jth word for document n, like so from the graphing model, we know that okay, Z and G, of course, it is related to theta n, right? And also related to the word, the specific word is samples, right? So its Markov blanket only includes the theta n and WNG. Right? So when you perform a mean field update, you just need to take a logarithm of the conditional probability of Z and G given theta n, right? From here. And also the likelihood given Z and G, you sample W and G, which is this guy. Right? And then you take a logarithm, you take expectation. Right? All the other conditional probabilities can be omitted because they do not contain Z and G. They're constant to Z and G. You don't need to care about that. So if you take a logarithm, this is multinomial. So remember, this is a product, right? So it is from k to big K, and you got theta n k to the power of Z and G k. You take a logarithm, you just move Z and G k in front of it. Okay. And similarly, this guy is just a bunch of products. If you take a logarithm, you just move the power to the front, right? But here we just merge the terms, so you got summation over k here and summation over v here. And then you take expectation because it's expectation under other variables that will include theta and also the beta. So you take expectation. Once you calculate expectation, you normalize this. And this is corresponds to a multinomial distribution again. Okay. How can we see that? If you take a look at arbitrary multinomial distribution, say z given alpha, so it is a, suppose you have a k dimension, right? So it is a alpha k z k, right? So if you write down as exp form, it will be just a logarithm of this guy. Right? If you take a logarithm, you see that this is essentially a summation of k to small k from 1 to big K, zk, logarithm of k. Right? So you can see that the form here matches, right? So from this form, you can immediately say, okay, my updated posterior corresponds to a multinomial distribution. And what I need to do is just to identify the parameters of multinomial distribution, which is proportional to the term, the coefficient multiplied by z and k. So what you need to do is just to normalize this term. So phi mgk is normal, is proportional to this guy. Any question? It's pretty straightforward. But again, I will highly recommend you guys to derive these things by yourself. Right? So the update of theta n follows the same way, but you just need to be sure that you do not miss the variables in the Markov blanket. Right? We know that theta n, of course, it should be appear in the prior of theta n, but also the theta n governs the distribution, the generation of all the topics for all the work, right? Because theta n connects to all the nodes inside this document. So you need to take logarithm of the prior of theta n and also the conditional probability of z and j given theta n for all the j belongs to the document n, right? That's why there is a summation here. Again, it's just to involve Markov blanket. And if you do this and take expectation and take exponential, you'll find that this guy corresponds to Dirichlet distribution. It matches Dirichlet distribution. And what you need to do is just find this coefficient, it rightly corresponds to the parameter of your Dirichlet distribution you are updating posterior. And similarly, you can update Q of beta k, and the Q of beta k, because it involves all the documents in your corpus, the collection of documents, because it determines every word in every document your collection. So the Markov blanket will involve the prior of beta k and also other words in the whole data. That's why you've got summation over the documents, summation over the words, and this is just vocabulary. And then you do the mean field variation inference update. You find that it follows another Dirichlet distribution. And then the remaining thing is just to calculate expectation, the required expectation to obtain the corresponding parameters in the updated version posterior. And because Q of z and gk, it is a multinomial distribution, it's relatively easy. And for theta n and the beta k, they all follow the Dirichlet distribution, right? So if you want to calculate the expectation of the logarithm of a Dirichlet variable, how do you calculate that? Don't worry, there's a form to calculate that. You're going to involve some like the gamma function, that is derivative of a gamma function, and those things can be checked out in any statistical book or Wikipedia. So you don't need to worry about that. And once you have finished updating of your variational posterior of beta, theta, and z, right? You just shove your current Q beta theta z into your variational evidence lower bound. And to calculate evidence lower bound, you will get objective function with respect to the hyperparameters, which include alpha and eta. Okay? And then you can just calculate gradient, and then use any optimization package you want to optimize that beta, and just do this repeatedly. And again, this will involve some dynamic function. If you're interested, you can try to derive that. It is a bit lengthy, but it's not hard at all. And of course, because your Dirichlet prior parameters alpha and eta or needs to be positive. So when you run LBFGS, you might add some like bounding constraint, right? It must be positive. And just do this. Okay, so sorry, we're running out of time, but just to give you a concrete example to showcase how Bayesian modeling is used in practice and how we conduct variation inference on that, it turns out to be very useful. Okay, thanks everyone, and let's see you on next Tuesday.